I'm going to talk largely about humans, but partly about animals. And I'm going to look for the best ways of walking and running and jumping. Now, the human body and animal bodies are awfully complicated. But the models that I'm going to show you are very, very simple. They're deliberately simple. I think it's best that way, because I believe that simple models can show us the basic principles much more clearly than complicated ones could. Now, they really are simple. I think that walking looks something like this. Here you've got a mathematical person walking along with a trunk and two rigid legs. And while a leg is straight, while a foot is on the ground, the leg remains straight. That means that as the body moves forward, it pivots around the foot. The body travels along in a series of arcs of circles, rising and falling. Now, that's simple, but is it realistic? Well, let's have a look at some photographs. Here we see walking. You see that while a leg is on the ground, it's pretty nearly straight. And if you look closely at Nicola's head against the brickwork, you'll see that her head is rising and falling, like the model. So the model's in some sense realistic. What can we do with it? Well, let's ask it a question. I find that if I try to walk as fast as possible, I simply cannot walk faster than 3 meters per second. Now, that's not just because I'm old and decrepit. Adults, in general, cannot walk faster than 3 meters per second, and the top speed is lower for small children. Now, why can't I walk faster than that? Let's ask the model. Here we've got the model again, traveling along at speed u, and the length of the legs is h. Now remember that the body is moving along through a series of arcs of circles. And remember that when a particle's moving around a circle, it's got an acceleration towards the center of the circle. The acceleration is speed squared divided by radius. In this model, that is u squared divided by h. Look at the picture on the right with the leg vertical. The body's got an acceleration u squared over h downwards towards the foot. Now, what's causing that acceleration? The foot isn't stuck to the floor. There's nothing to produce that acceleration except gravity. So that downward acceleration cannot be greater than gravitational g. U squared over h can't be more than gravitational g. Rearrange the thing. The speed can't be greater than the square root of gh. Let's put some numbers in. Gravitational acceleration, approximately 10 meters seconds to the minus 2. Leg length for a human adult, 0.9 of a meter. Square root then of 10 times 0.9, square root of 9. Isn't that good? 3 meters per second. Our mathematical model tells us that I cannot walk faster than 3 meters per second, and in fact that's my top speed. Now the model tells us something else too. I've got a small grandson, and when he and I walk along together, I may be walking, but he may have to jog to keep up. Why can't he walk as fast as I can? Because h, leg length, is less for him than it is for me. So square root of gh is less. His top walking speed's less. Now, u squared over h can't be bigger than g. Think of that another way. U squared over gh can't be bigger than 1. And that quantity, u squared over gh, speed squared over leg length times gravity, we call that the Froude number. The theory says you can't walk with a Froude number greater than 1, and we'll be coming back to Froude numbers later. But look at this. Oh dear. Mathematics says these chaps can't walk faster than 3 meters per second. They're actually doing the racing walk, walking at 4 meters per second or possibly even a little more. How are they doing it? Look at number 629. Look at the way he's wiggling his bottom. Now what he's doing is, as he walks, he wiggles his hips in such a way that his center of mass doesn't rise and fall so much, as the theory says. So, he isn't walking according to the assumptions of the theory. The theory doesn't apply to him. Athletics is the art of cheating without actually breaking the rules. So far, we haven't talked about optimization. We haven't talked about what's best. I've only talked about what's possible. Let's go back to another observation. If I've got to walk, if I'm going to walk and not run, then I cannot walk faster than 3 meters per second. But give me a choice between walking and running, and I'll break into a run at 2 meters per second. Now, why do I do that? One possible reason is that it might cost less energy to run at speeds above 2 meters per second and to walk at speeds below 2 meters per second. Let's find out whether that's true. Here we've got an experiment in which a woman's oxygen consumption is being measured. If we measure her oxygen consumption, we can work out how much energy she's using. She's walking on a conveyor belt, which is moving backwards into the picture. She's walking forwards out of the picture, so she's staying stationary in the laboratory. And that means we can attach her to our oxygen analysis equipment with that vacuum cleaner tubing. All the air she breathes out is taken away and analyzed. We find out how much oxygen she's using, that way how much energy. And what we find is that at speeds below 2 meters per second, walking is more economical than running. At speeds above 2 meters per second, running is more economical than walking. Oh, and I should perhaps explain that when the experiments I was talking about were done, they weren't done with someone carrying a jar on their head. So there's an energy-saving advantage in changing from walking to running when your speed gets to 2 meters per second. Let's turn from physiology to mechanics to see whether we can explain why that change occurs. Here we've got a graph showing schematically the forces that act on the ground when you walk. First of all, you put your left foot down on the ground and the force rises and falls, rises and falls. You've got a two-humped pattern of force. Then, before the left foot rises, the right foot comes down, and again you get a two-humped pattern of force. Total force when both feet are on the ground is shown by the broken lines. You see the force rising and falling in the course of a stride. When both feet are on the ground, the force is greater than body weight. When only one foot is on the ground, the force is less than body weight. And that's exactly what you need to give that rising and falling that we saw happen when you walk. Well, that's the schematic pattern. Let's look at real forces in walking and running. Here we've got a series of graphs of force against time produced by having people walk over a force-sensitive plate set into the floor. In each case, we've got the force produced by the left foot, shown with a solid line, and the force produced by the right foot with a broken line. At the top of the picture, you see the pattern of force that you get in slow walking. The two-humped effect is very slight. The force rises, plateaus, and falls again. Walk a bit faster, and that's the second picture from the top. And now we've got more of a two-humped effect. Third picture, we're going faster still, very markedly two-humped. The faster you walk, the bigger the force fluctuations you need to produce the up and down movement. But then when you run, things change completely. When you run, that's the bottom record, instead of two-humped patterns of force, you've got one-humped patterns. Ignore the little blip, which is where the heel hits the ground. Ignore that, and you've got essentially a single-humped pattern of force being produced by each foot. And there's another difference. In walking, each foot is on the ground for more than half the time. So there are times when both feet are on the ground simultaneously. In running, each foot is on the ground for less than half the time. So there are times when both feet are off the ground. So we've got these differences in pattern of force between walking and running and between different speeds of walking. And if we're going to be able to explain these patterns, we're going to have to be able to describe them. And I'm going to use two parameters. One of them is easy enough. It's what I call the duty factor. Now, the duty factor is the fraction of the stride for which each foot is on the ground. In walking, each foot is on the ground for about 60% of the stride. So the duty factor is 0.6. In slow running, each foot is on the ground for about 0.35 of the stride, so the duty factor is 0.35. The other thing we want to be able to describe is the one-humped or two-humped patterns of force. So let's try a little trick. Let's look at this function here. F is equal to something times the cosine of an angle minus a constant q times the cosine of 3 times the angle. Let's plot out half a cycle of that function for different values of the constant q. If we make q equals 0, then that's the second picture from the left. Then obviously what we get is half a cycle of a cosine curve. If we give q positive values, we get two humped curves, as in walking. And the bigger the value of q, the more markedly two humped the pattern is. If, on the other hand, we give q negative values, then we get a bell-shaped curve, and force patterns of running are rather like that. I'm going to call q the shape factor, and we'll use the duty factor and the shape factor to describe different kinds of walking. We'll make a model walk like that. Here is a simple model of walking. A mass walking along on legs. We won't bother to give the legs knees. We'll just give them a sort of hydraulic actuator so that they can get longer or shorter if necessary in the course of the stride. And the actuators will have, under force control, we'll arrange mathematically for those actuators to exert the patterns of force that we want to happen. So let's look at this model. Here's our model. We'll keep it simple to start with. We'll ignore the mass of the legs. And we'll consider a stage when just one of the feet is on the ground. Here are the forces then acting on the model, the weight, and the vertical and horizontal components of the force exerted by a foot. We'll write some equations. First of all, we'll say the horizontal force equals the vertical force divided by the tangent of the leg angle. Now, what that is saying is that the resultant force on the foot acts in line with the leg. And we observe that to be true in real walking. Then the horizontal acceleration is equal to the horizontal force divided by the mass. The vertical acceleration is the vertical force divided by the mass minus gravitational acceleration. We'll specify the patterns of force exerted on the ground by the foot, specify how Fy varies with time using our duty factor and our shape factor. We'll put the thing into a computer, and this model is so simple that I used our home word processor to do it on. And we'll calculate how much work the actuators have to do as the model walks along. Now, at some stages of the stride, the actuator will be pushing on the ground and getting longer. It'll be doing work. At other stages of the stride, an actuator will be pushing on the ground, but getting shorter. In effect, it'll be doing negative work, acting as a brake. Now, I'm only interested in the positive work, and here's why. Suppose I climb a mountain. I do a lot of positive work, giving myself potential energy. But then I come down again. I lose the potential energy. My leg muscles are doing negative work. But that doesn't mean that all the energy is flowing back into my body. I don't feel ever so refreshed. To work out how much energy, how much chemical energy, food energy the muscles are going to use, we're going to have to look at the positive work done in the course of a stride. And what's that going to be? The work done in a short interval of time is equal to the resultant force on the actuator during that interval multiplied by the change in the length of the leg. So that's roughly how the mathematical model works. We're actually going to have to make it a wee bit more complicated. We're going to have to take account of the mass of the legs, and also we're going to have to take account of the springiness of the legs. I've done some rather gruesome experiments with amputated feet, which show that your foot is a bit springy, and the tendons of your leg muscles are a bit springy, and this affects the work that the muscles have to do in the course of the stride. So we'll have this rather more complicated model with a spring in it, and of course that means that our equations are going to become a bit more complicated. But let's see what that tells us. We're going to have a graph, and in this graph, on the vertical axis, we've got the shape factor. On the horizontal axis, we've got the duty factor. Now, let me remind you what that means. Here we've got the same graph, and round it we've got sketches showing the patterns of force exerted on the ground in different sorts of gaits. Suppose you're down at the bottom right-hand corner of the graph. Then you've got a big duty factor. That means that each foot is on the ground for most of the time. You've got a low shape factor. That means that you've got a one-humped force pattern. So this is what the pattern of force on the ground looks like. Left foot, right foot, left foot. Go up to the top right corner. We've still got a big duty factor, but we've now got a high shape factor, so we've got the two-humped pattern of force. Over on the left-hand side of the graph, we've got a low duty factor. So we've got the one-humped patterns of force with low duty factor, or a two-humped pattern of force with low duty factor. Between them, these two parameters are giving us a whole range of patterns of force, which is represented by the space on the graph. Now let's turn to the slide again. The contours on the graph show the energy cost calculated from the model. And you see that I've colored in two areas where the energy cost is low. In one of these areas, up at the top, we've got high shape factor and a duty factor of around a half. That's plainly walking. Down at the bottom left, we've got low duty factor and low shape factor. That's running. So here are two gaits where the energy cost is low. Now, if we were to look at the finer detail of the contours, we'd find that we could actually get slightly lower energy cost by using the run than the walk. But this particular graph is drawn for a speed which is a fast walking speed. So what's wrong? Have a look at that running minimum again. Do you see that that's telling you that you can get a low energy cost by running if you make the duty factor very, very low, if you have your foot on the ground for only a tiny fraction of the stride. Now, the shorter the time that your foot's on the ground, the bigger the force it's going to have to exert so that the average force over a complete stride outbalances body weight. What this graph is telling us is that you can run at this walking speed with ever such low energy cost, but the foot's on the ground for such a small fraction of the time, the forces are going to be so big that you're going to break your legs. So plainly, that's not the best thing to do. But let's make a comparison now between different speeds. That graph was for just one particular speed. Let's look at similar graphs for a range of different speeds. Here you see the graphs and you see the speeds. Start off at 0.4 meters per second, a very slow walking speed. You've got a low energy cost for a walking gait. you've also got a low energy cost for a running gait just off to the left of the graph. Walk faster at 0.8 of a meter per second, you've still got your walking and running minima. Go faster, you see the walking minimum moving further and further up the graph until when you go above 2 meters per second, that minimum has disappeared off the top of the graph. And I should explain that there isn't the possibility of walking with higher shape factors than shown on the graph, that the top of that graph represents the highest possible shape factor, because if you had higher shape factors, then you'd start getting negative forces on the ground. So let's look at that graph again. As we walk faster and faster, the walking minimum is moving to higher and higher shape factors. And in fact, we do that when we walk. Our pattern of force becomes more and more two-humped. And then look at the running. The running minimum is starting off very far towards the left of the graph. It's moving in towards the right, coming to higher duty factors. Higher duty factors, therefore lower forces. At the time when the walking minimum disappears, the running minimum moves into a region where the forces required are feasible. And so that's where we change from walking to running. So far, I've been talking entirely about people. Let's look at something different. I talked about me and my grandson. Here's a more extreme difference in body size. A cat and a rhino. Four-legged animals, and these four-legged animals have three gaits. We walk or run. Four-legged animals walk or trot or gallop. This particular slide shows galloping. Now, it's working out the speed at which a four-legged animal should change from a walk, from a trot to a gallop. That's a bit complicated and hasn't actually been done. But let's see if we can work out some general principles. How should the speed at which the cat changes gait relate to the speed at which the rhino changes gait? Now, here we've got both of them galloping. And I want you to notice that their movements are very similar. Enlarge the cat and slow down the tempo of its leg movements, and you could have movements just like the movements of the rhino. That reminds me of the concept of geometric similarity. Look at these triangles. 3, 4, 5 triangle and a 6, 8, 10 triangle. You can change one to the other by changing the scale of length. We describe them as geometrically similar. But there are other kinds of similarity. Look at those two musical rhythms. A long note followed by 4 short notes. we can make those two rhythms identical to each other simply by changing the scale of time. That leads to a more general concept. The concept of dynamic similarity. Dynamic similarity is similarity between patterns of movement. If you can make one movement similar to another by changing the scales of length and time and force, then your two movements are dynamically similar. And I'm going to suggest that, roughly speaking, the movements of a cat might be dynamically similar to the movements of a rhino in certain circumstances. What are the circumstances? In walking and running and galloping, the body is changing potential energy and changing kinetic energy. It seems reasonable to suppose that dynamic similarity will only be possible if the ratio of kinetic energy to potential energy is the same for the things you're comparing. Kinetic energy, half mass times velocity squared. Potential energy, mass times gravity times height. Cancel out the m's. Speed squared divided by twice gravity times height, or leg length if you like. And look, we've got half a food number. What this approach is telling us is that we can expect different sized animals to change, to move in dynamically similar ways whenever their food numbers are equal. We can expect our cat and our rhino to change from walking to trotting at the same food number, and from trotting to galloping at the same food number. The food numbers will be the same, but the speeds will be different because their sizes are different. Let's see whether it's true. Well, we won't look just at cats and rhinos. We'll look also at rats and horses and dogs and sheep. We find that the change from a walk to a trot happens at a food number of about 0.8. The change from a trot to a gallop at a food number of about 0.2 for all sorts of sizes of animals. Oh, and that, of course, links in to what I was saying earlier about the maximum possible walking speed being the speed that corresponds to a food number of 1, the maximum possible one. So far, I've been talking about walking and running. Let's go on and look at jumping. First of all, briefly, the pole vault. When an athlete does a pole vault, he or she runs up at high speed, plants the pole bends and recoils and throws the athlete into the air. Think about the energy. The athlete's running along at first with high speed, that's high kinetic energy. The pole bends, storing up elastic strain energy. The athlete rises into the air, gaining potential energy. What happens is that you get kinetic energy changed to elastic strain energy, changed to potential energy. And if you work out the energies, you find that, roughly speaking, the potential energy at the top of the jump equals the kinetic energy of the run-up. Now, that tells us that in order to do a good pole vault, you ought to run up as fast as you can with as much kinetic energy as possible. And pole vaulters do in fact run up at fast sprinting speeds, 10 meters per second or so. I wanted to establish that because I want to go on to talk about high jumping. And we're going to see whether the principles are the same. Now, one little point we need to get across. Look at the woman in the lower picture. She's doing the Fosbury flop. Look at the way she's bent over backwards. That means her center of gravity is actually somewhere out behind the small of her back. The height of her center of gravity from the ground is approximately equal to the height of the bar from the ground. And we're going to use that in a moment. But I'm not going to concentrate on what athletes do as they go over the bar. I'm going to look at what happens as they run up. Look at the pictures along the top. Here we've got an athlete seen in side view running up for the high jump. As he runs up, at the end of the run-up, he places his foot on the ground with the leg straight. The leg bends and straightens and throws him up into the air. Roughly speaking, he's using his leg like a pole vaulter's pole. But there's something strikingly different. He's running up remarkably slowly. Now this chap's good. He's only a few centimeters off the world record. But he's running up at only 7 meters per second. He could run up at 10 meters per second. He's actually only running up at 7 meters per second. He could run up with a whole lot more kinetic energy than he actually has. Now, why is he doing that? And the answer, I think, is the obvious one, that his leg isn't a pole vaulter's pole. His leg isn't just springy fiberglass. It's bones jointed together with muscles in them. And those muscles have properties that we need to know about. We're going to have a model like this, a model with a muscle in it. The athlete runs up at speed v, places a leg on the ground, the leg bends, stretching a knee muscle, and extends as the knee muscle shortens again, and throws the athlete up into the air. Very simple model that we're going to put into the computer again. But we need to specify what the properties of that muscle are. And here's what physiologists tell us the properties of muscles are like. A graph showing the force that a muscle can exert plotted against the rate at which it's shortening. Lengthening, of course, is negative shortening, so we've got lengthening over at the left-hand side of the graph. What this graph shows is that the faster a muscle shortens, the less force it can exert. On the other hand, if you stretch a muscle forcibly, you get enhanced force. So we're going to put a muscle with properties like that into our mathematical model. And here's what's going to happen. Our mathematical athlete is going to run up, place the leg, it's going to bend and straighten again, throw the athlete up into the air. The center of mass is going to travel along a parabola, and we're going to use the height to which the center of mass rises as an estimate of the height of the jump that the athlete does. But we'll also look at long jumping, and we'll use the horizontal distance that the center of mass travels before it hits the ground again. We'll use that as a rough estimate of the length of the jump. Let's put this into the computer. And we will look at what happens when we run up at different speeds and set down the leg at different angles. Look at the left-hand graph, which refers to long jumping. On the horizontal axis, we've got speed, ranging from a slow jog to a very fast sprint. On the vertical axis, we've got the angle at which the leg is set down. The contours represent the length of the jump. And down in the bottom left-hand corner, we've got jumps of negative length, your athlete's jumping backwards. But if you look to see what the longest possible jumps are, those are coming out from the model as something over 8 meters, which is realistic. You see, to get the longest possible jump, you've got to run as fast as possible. That's what you'd expect. Run as fast as possible, set down your leg at about 65 degrees, and that's about what long jumpers do. But now let's look at the right-hand graph, which represents high jumping. Same axis, but this time the contours represent the height of a jump. And do you see, it's no longer advantageous to run as fast as possible. You get the highest jump now by running at a moderate speed, about 7 meters per second, which is what good high jumpers actually do. Again, the model tells us that we should set down the leg at a rather shallow angle of about 50 degrees, and that's what high jumpers do. Now, you could suspect me of cheating. The parameters for muscle properties that I've put into the model, they're not very accurately known. So just to check whether I've been lucky in getting the right answer, I've tried varying the parameters a bit. And it doesn't make a whole lot of difference. I can vary them within quite a wide range. I still get about the same answer, that the best thing a high jumper can do is run up at about 7 meters per second, which is what high jumpers actually do. Now, I've shown you a series of simple models. Simple models of very complicated structures. There's a complicated structure for you. Now, although my models have been simple, I believe that their simplicity helps us to see the basic principles human and animal movement, the basic principles of walking and running and jumping.